Now let's delve into the urinary system, which provides a very important mechanism of homeostasis for the body in that, one, it excretes or removes organic waste from body fluids. It will then eliminate these body fluids as urine. And we also have homeostatic regulation of blood volume and solute concentrations, first of all, by regulating the amount of fluid that is lost and the amount of solute concentrations of things like sodium, potassium, hydrogen, and other things that we don't really need in the urine. And also we'll see that the kidney has hormonal functions. So for example, it produces erythropoietin, which is going to affect our blood viscosity by increasing the amount of formed elements in the red blood cells that will be produced. And it will produce something called calcitriol that will help us or allow us to absorb calcium in the intestinal tract. All right, so here is a quick overview. We have the kidneys themselves, and the kidneys are going to be producing the urine. Then we have the ureters, which are the tubes that lead from the kidneys to the urinary bladder. And then we have the urethra, which is the exit point from the bladder to the outside of the body, and this is where urination, also known as micturition, occurs. So one quick thing about the kidneys, you'll notice that we have our renal arteries and renal veins and our ureters, and they are going to be entering or exiting the kidney at the renal hilum, which is this indention here. Now, another organ that's not part of the urinary system, but it's closely associated with the kidney, and in humans sits right on top of it, is the adrenal, or the adrenal gland up here, which is also known as the suprarenal gland in some cases. All right, so one of the things we know the kidney does is it produces urine. And then, of course, from there, we're going to have the ureters be the pathway to the urinary bladder. And this is a muscular sac that fills throughout the day. And then when it gets filled, then the person can micturate or urinate and void that excess urine through the urethra. All right, so one of the things we've already talked about is the regulation of blood volume and blood pressure. We know the volume will be adjusted by the water lost in urine. We also know that we will have the release of erythropoietin, and that will increase the amount of formed elements in the form of red blood cells in the blood. We also have renin, and renin is a hormone that's part of the renin-angiotensin-aldosterone system, and this is going to promote increase in blood pressure and retention of fluids. So if you remember, aldosterone is going to promote the conservation of sodium by the kidney, and where salt goes, then water follows. So we will also have retention of water at the kidney when we have aldosterone. And remember, aldosterone is linked with antidiuretic hormone as well. And when aldosterone is produced, antidiuretic hormone is also produced. We will see that there is a sympathetic regulation of the kidney. We will also see that the kidney will regulate plasma ion concentration, so sodium and potassium, chloride ions. And we'll also see that it produces calcitriol, which will help us to absorb more calcium at the intestinal tract. And so calcium levels can be regulated by the production of calcitriol, how much the kidney produces. All right, another thing it does is it helps stabilize our blood pH because it will control loss of hydrogen ions and bicarbonate ions. We'll also see that it will preserve some very valuable nutrients. So the kidney is like a big filter, and we'll see the individual filtration units called nephrons. And they're very good at filtering everything. Just about everything, with the exception of plasma proteins, will be filtered into what we call the filtrate, which will eventually become the urine. But it's so good at filtration that somewhere along the way, we're going to have to pick back up those important things. So, for example, glucose, amino acids, these things will be picked back up later on in another part of the nephron that will reclaim these important nutrients while excreting organic waste. So some organic waste actually don't quite make it through filtration, so they will be excreted at the distal part of the nephron, the part that doesn't do the filtration. And it's also very important for inactivating or excreting drugs that we've taken. So any kind of drugs, pharmaceuticals that will then be excreted by the kidney. And in this way, it will help in the liver assist in detoxifying poisons. All right, so we've got basically all of this is word slides that are going to describe exactly what's in the picture. So here we have a transverse section. Here is our kidney. We will see that we have a renal cortex. We have a renal medulla, which is full of these renal pyramids. We'll talk about those in a little bit. And then we're going to have a space between where urine will collect, and we'll talk about that in a bit more detail later on. We have a fibrous capsule that surrounds the kidney, and then around that we have, if you recall, the kidney's retroperitoneal. So here's your peritoneum up here. Well, actually, this is your peritoneum, and this is your renal fascia here. So it has its own renal fascia that's going to surround what we call perinephric fat. And this perinephric fat is really important for padding that kidney. So we have the fibrous outer capsule of the kidney, it's part of the organ itself. We have the perinephric fat, which is going to pad the kidney and keep it from bouncing around and also cushion it from impact. Then we're going to have the renal fascia above that, or I should say superficial to that. And as you recall, all of this is going to be behind the peritoneum. So here's our pancreas, which is also a retroperitoneal organ. You can see the peritoneum here, and you can see how it winds around these other organs like the stomach, the spleen. And here's your spleen, and here's your peritoneum, and you can see that the kidney is behind it. So the kidney is locked to the back body wall and is not contained within the peritoneum. All right, now if we look at the kidneys as a whole in the abdominal cavity, you can see immediately that the right kidney is lower than the left. And that is, if you think of the location of the liver is going to be occupying this space, and that right lobe of the liver is quite large. So the kidney is displaced down a little bit, or inferior a little bit, to accommodate that right lobe of the liver. Whereas on this side, we're going to have the left kidney up a little bit higher. Remember, the stomach is here, and the spleen would be over here. Now we can see our arteries coming in. Here's our renal artery coming into this renal hilum, and here's our renal vein that will be exiting the renal hilum, and here we have our ureter, which is going down into the urinary bladder. Alright, so the adult kidney is about 10 centimeters long, about 5.5 centimeters wide, and 3 centimeters thick, and weighs about 150 grams. And as we've said, the hilum is the point of entry for the renal arteries and renal nerves, and is going to be the point of exit for our renal vein and our ureter, as we saw in the previous picture. So let's actually look at the sectional anatomy of the kidneys. So we'll talk about all of these slides in this picture. All right, so let's start with the renal sinus. And the renal sinus is the space that contains all of these passageways. And these passageways are going to conduct the urine to our renal pelvis. You probably remember our renal pelvis, which is then going to conduct it into the ureter. So the renal pelvis is this giant funnel that's going to be collecting up urine from all these smaller funnels. So we have a major calyx. Major calyces are larger funnels that are going to dump into the renal pelvis. And then we have minor calyces that are smaller funnels that are going to dump into the major calyx. And remember, this is a three-dimensional structure, so here's another minor calyx would be in here. Here's the opening to it. Remember, we've cut this in longitudinal section here, so coronal section, if you will. And one of the things that you will notice is that all the space in here, all of this is the renal sinus. Your book doesn't really do a good job pointing it out. It just points to this as the renal sinus. But all of this space in here is part of that renal sinus. We see we got a little bit of fat in here. We got some blood vessels in here. We've got all the passageways from these, which are going to produce the urine. We'll talk about that in a bit. But all of these are contained within the renal sinus. So our minor, major calyces, our renal pelvis, and then of course from the hilum comes the ureter, and that's where the urine will be conducted out of the kidney. Now let's talk about the structure of the kidney. Below the fibrous capsule, we have the renal cortex, and that's this stuff right here. Now the renal cortex has these extensions, these column-like extensions down toward the center of the kidney. And these are called renal columns. And all of this here, anything from here to here is going to be the renal medulla. So all of this is the renal medulla. All of this is the renal cortex, this pinkish stuff in the picture here. And then we have these renal columns that have very similar consistency to the renal cortex, but they're still within the renal medulla. But the renal medulla is characterized by the presence of these renal pyramids. And this is where a lot of the work of the kidney is going to be done. And so the renal pyramids, there are anywhere from 6 to 18 per kidney. So here's a renal pyramid. They end in these little renal papillae, and this is where the urine is going to be dumped into the minor calyx. And then we're going to have a kidney lobe, and that's going to consist of a renal pyramid and about half the renal column that surrounds it on either side. So this is our renal pyramid. All right, here it is in real life view. Here's our cortex, some renal columns, renal pyramids here. The darker stuff is the renal pyramids. Here's a minor calyx, here's a major calyx, and here is the renal pelvis. Here's a major calyx with 2 minor calyces basically leading off of it. And you see how the renal papillae are in contact with this minor calyx. Here's our ureter. All of this space in here that contains the major and minor calyces and all this fat inside and blood vessels, that is the renal sinus. All right, so nephrons are the functional unit of the kidneys. These are the things that are going to be doing the filtration, the absorption, resorption, or reabsorption, either term is correct, and the secretion. So we will see a lot of things are going on in the nephron. This is the functional unit of the kidney. This is where the urine production begins. And we'll see there are 2 types of nephrons. And we'll talk about those in a little bit of detail later on. They both have very similar functions, but one type is really, really important for concentrating the urine. So we'll talk about them in a little bit more detail. But just to point out now, the nephrons are the functional units of the kidneys. And of course, to understand that these are things that are going to be filtering blood, we've got to understand the blood supply to the kidney. So we got about 20 to 25% of our total cardiac output will be going to the kidney, which is going to be having about 1,200 milliliters of blood flowing through it each minute. This is quite huge. And as we know, the kidney is going to receive that blood through the renal artery. Now let's talk a little bit more about some of the other blood vessels that are in there. So all of these things, these slides, are going to be germane to this picture. So here we have our renal artery, then that's going to branch into segmental arteries, which will then branch into interlobar arteries, which will then turn and become arcuate arteries. And then we will have these called cortical radiate arteries that are going to radiate into the cortex. It is these cortical radiate arteries that are going to be supplying our nephrons and bringing blood to the nephrons. And the blood that is coming to the nephrons will be coming through what we call an afferent arteriole. And the afferent arteriole will be supplying an individual nephron. And we'll see a picture of it in a little bit. So here we have our cortical arcuate, our arcuate and our cortical radiate arteries here. And what we will find is what they've done here is they've shown just a structure called the glomerulus, which is the major filtration structure along with the surrounding capsule of the nephron. Now, the nephron has 2 parts. It has a renal corpuscle, which is comprised of the glomerulus and this capsule that surrounds it. And then from the capsule comes this long renal tubule that has 3 major parts. This is actually part of the collecting duct over here. But all of this is a nephron. And so what they've done is they've shown one nephron. This is called a cortical nephron because most of it is in the renal cortex. This one is called a juxtamedullary nephron because the top part of it, the glomerulus, the renal corpuscle, and the top part of the renal tubule is located in the cortex. But then you have this long part of it called the loop of Henle, or the renal loop, the loop of Henle, the nephron loop, dips down into the cortex, into the medulla, deep into the medulla. So these are called juxtamedullary nephrons because they are next to, juxtaposed, if you will, to the medulla, hence juxtamedullary. And all of these others are just what we call the glomerulus, and they've taken the rest of the nephron away, because what they want to show here is the blood perfusion through the afferent arteriole into this glomerulus. So from there, we're going to have a huge bunch of what we call peritubular capillaries. When we come over here, we'll have even another part of blood supply that we call the vasa recta, because it just means straight vessels, and we'll see that they'll follow this loop of Henle, and it's a very straight bunch of blood vessels. And eventually that will feed into this venous return system, which is very similar. We're going to have an arcuate vein, we're going to have an interlobar vein, we're not going to have a segmental vein, but then we'll have the renal veins and so forth. So when we talk about the nephron, we can once again talk about these terms, and it's probably a little bit easier to look at them. So here we have the afferent arteriole bringing blood into this sort of network of about 50 capillaries. And this is where the filtration will occur, in this area right here called the renal corpuscle. So all filtration occurs in here. Now from this point on, we're going to have produced a filtrate, which will eventually become urine. So that filtrate will then enter into the renal tubuli. Now one thing I would like to note here is that this usually is folded around the renal corpuscle. They have unfolded the renal tubuli so we can look at it in more detail. So they've kind of laid it out for you. So at the beginning we have this little convoluted part of the renal tubuli that is called the proximal convoluted tubuli. And then we're going to have it lead into the straight part, which is basically called the loop of Henle, H-E-N-L-E. So the loop of Henle. So this is the loop of Henle, which has a thick part and a thin part. And what makes it thin is that we've transitioned from a cuboidal epithelium into a squamous epithelium here. And then once we have ascended back up the loop of Henle, then we get to what's called the distal convoluted tubuli. And notice that this will be all folded back onto this so that the end of the distal convoluted tubuli will actually pass through this bifurcation here where we have the entrance of the afferent arteriole and the exit of the efferent arteriole. And we can see that we have quite a bit of histology differences depending on where we are. And that will be related to the function of each part of this nephron. So we will have this capsule, this renal capsule, and the part that surrounds the glomerulus is called the renal capsule, and that is basically also called Bowman's capsule. So if you hear it called Bowman's capsule, it's the same thing. And that is this outer part of the renal corpuscle, and it's what surrounds the glomerulus. So the renal capsule and the glomerulus together make up the renal corpuscle. And we will see that we have simple squamous epithelium here. And it not only surrounds the outside, but it will surround the glomerulus itself. And we have specialized cells that surround the glomerulus that are called podocytes. We'll talk about them in just a bit, but they're very important and part of the filtration membrane. Now from there, we will have a lot in the proximal convoluted tubuli. We will have a lot of reclamation or reabsorption of important nutrients that were filtered out at the glomerulus. So things like glucose and certain ions and these kinds of things will be reabsorbed. So they will be taken out of the filtrate in the proximal convoluted tubuli and returned to the interstitial fluids that will then be returned to blood circulation. Now, we're going to have a very important process go on in the loop of Henle that we'll talk about in a lot more detail later on. We'll see that there is a passive reabsorption of water by osmosis. So water will leave the loop of Henle, the descending limb, through osmosis. We will have some water resorbed here at the proximal convoluted tubuli as well. And then we will have, as we come up the ascending limb of the loop of Henle, the thick part of the ascending limb, we will see that we have a lot of solute resorption, especially sodium and chloride. And this is going to be very important because it's going to make the interstitial fluid between the two loops, or the two halves of the loop, I should say, the descending and ascending parts of the loop, it's going to make it very salty in there. And we'll see that becomes important later on. Now, the distal convoluted tubuli is where we're going to have excretion of a lot of products. We will have some selective resorption here, but we'll have more excretion than resorption. And we'll also have a lot of excretion of things like bicarbonate ion, hydrogen ion drugs, inactivated pharmaceuticals, and so forth. Another thing we will have, depending on what your blood plasma levels are, we will have some selective reuptake of water as well. So we will have channels called aquaporins that will be inserted into the distal convoluted tubuli under the influence of antidiuretic hormone, and that will cause us to resorb a lot more water, so it does not leave as urine. So it will not pass out of the distal convoluted tubuli into the collecting duct. Now, all the distal convoluted tubules will empty into a collecting duct, and many nephrons will empty into a single collecting duct, and we'll look at that in a little bit more detail. So, suffice it to say, since we have different processes going all along here, we have different types of histology. So our Bowman's capsule on the outside is going to have this simple squamous epithelium. We will see, when we look more closely at the glomerulus, we're going to see special cells called podocytes. When we come in here, we're going to have cuboidal epithelium with lots of microvilli because we're going to have a lot of absorption, some secretion in here. And then when we go to the descending limb, we're going to have a lot of osmosis of water out into the interstitial fluid this way to be recaptured. We're going to have some squamous cells here. We're going to have some cuboidal cells over here in the ascending thick limb, and this is why it looks thicker. The luminal diameter between this and this are actually pretty similar. So then when we get into the distal convoluted tubuli, we will have all kinds of secretions, ions, acids, drugs, toxins, some reabsorption of water, as we've said, some reabsorption of some of these solutes. For example, sodium ions will be under the control of aldosterone. So if we have a high aldosterone concentration, we'll resorb more sodium ions. And when we have, for example, antidiuretic hormone, will have more resorption of water. So this is all under the control of hormones and is variable. So here we have some cuboidal cells with a few microvilli. So this is just sort of a quick overview of what a nephron looks like and what it does. Now, as we've said, the glomerulus is about 50 intertwined capillaries, and a glomerulus literally is a Latin term for something like a ball of yarn. It's this intertwined stuff. And we're going to, as we've said, we have seen the afferent arteriole come into the glomerulus, and the efferent arteriole will leave the glomerulus. So basically, it will flow into what are called the peritubular capillaries, and these will then drain into our small venules and return to the venous system. So let's look at what's going to go on in the renal corpuscle. This is where filtration occurs, and it occurs only in the renal corpuscle. And that really does sound like a great test question, doesn't it? That filtration occurs only within the renal corpuscle and nowhere else within the nephron. So this is going to be due to our hydrostatic pressure of blood, and we talked about that before when we talked about capillaries, and we're going to go into a lot of detail in the mechanism of how filtration and how some of these other processes work within the kidney and within the nephron. But what we're going to do is we're going to produce a solution that is virtually free of all proteins. It's going to be very similar to blood plasma, except without the proteins. So we're going to have what we call hydrostatic pressure coming into this glomerulus, and the glomerulus, we will see, is going to have fenestrated capillaries. And we will see it actually has a 3-layered filtration membrane that starts with these fenestrated capillaries inside, and then we're going to have a dense layer, and then we're going to have this extra set of cells outside of it that we talked about, and these are going to be continuous with that simple squamous cells that make up Bowman's capsule, but these are going to have special feet, and these foot-like extensions will interlock with one another like this and create filtration slits. And these cells, because of their foot-like extensions, are called podocytes. And we'll see some examples of them later on. We'll see a picture of them. But we're going to have this very nice 3-layered filtration membrane that is going to occupy the space within the renal corpuscle and will be consisting of the glomerulus, the endothelium of the glomerulus, with this dense layer and these podocytes. All right, so the renal tubule will come off of the glomerulus. And so it's going to resorb any organic nutrients that enter into the filtrate. So we're also going to resorb quite a bit of water in the filtrate, 90% or more. And here's the thing, if we just got rid of everything that we filtered out and the glomerulus was the end of the process, we would lose a lot of water. We would dehydrate within hours, pretty much. So we got to reclaim a lot of that water, and we would also lose very valuable nutrients like glucose and amino acids. So we're going to have some recapturing of those important things. So we're going to have a resorption of 90% or more of the water in the filtrate within the renal tubule. We will also secrete waste that didn't get into the renal corpuscle and through the glomerulus during filtration, and these will be very, very small things, that some of which will be under hormonal control, some of which will be things like drugs, some of them will be just other things that were small enough or large enough, not to be filtered out, so they have to be excreted. All right, so we have talked before about the renal tubule. We have our proximal convoluted tubule that will then dip into the nephron loop or loop of Henle, and then the loop of Henle will join with a distal convoluted tubule. And we've seen that in the picture. So here it is, just to remind ourselves. Here's our renal corpuscle. Here's our glomerulus. Here's our proximal convoluted tubule, our loop of Henle, and our distal convoluted tubule that will then lead into a collecting duct. And what's important to note here is that this thing is unfolded. So I want to reiterate that in reality this thing would be folded back upon itself so that the distal convoluted tubule will have a junction with the afferent and efferent arteriole over here at the renal corpuscle. And this is going to be very important, or right next to it, I should say. And this is going to be the source of regulation of a lot of what goes on within the nephron. So a lot of our control mechanisms for what's going on in the nephron will be due to a bunch of cells that we're going to see called the juxtaglomerular complex that will be right in this area here. And we'll talk about that a little bit later on. All right, so we can see that the filtrate, that is the stuff that we filter from the glomerulus, is going to become our tubular fluid. And it's going to change composition as it goes through the rest of the tubule, the nephron. So the proximal convoluted tubule, the loop of Henle, and the distal convoluted tubule. So we'll have a gradual change of composition in the filtrate as it moves along this tubule. And so it's going to, the activities, as we said, such as resorption, excretion, they're going to vary within each segment of the nephron. So as we know, the nephrons are going to enter into a collecting duct, and this is going to carry the tubular fluid away from the nephron. And one collecting duct will receive fluid from many nephrons, and the collecting duct will begin in the cortex, because this is where the distal convoluted tubule will contact it, and then it'll descend into the medulla, down through a papillary duct that drains into a minor calyx. As we've seen sort of the gross architecture of the kidney, we can see that the collecting ducts are going to extend from the cortex down into the renal papilla. This is basically part of the renal pyramid, and that's going to be in the medulla. All right, so here's a collecting duct. All of these are distal convoluted tubules that are feeding into it. And we're going to have some resorption of water in the collecting duct, again under the influence of antidiuretic hormone. And we're going to have secretion of things like sodium, potassium, sodium secretion under once again, aldosterone, and potassium, hydrogen, and bicarbonate ions. And we'll see that there's certain types of cells. There are intercalated cells and principal cells. We'll get into those a little bit later, and these are going to make up cells of the collecting duct. And these are going to be important because they will be responsible for regulating the amount of bicarbonate and hydrogen ion. And we'll get into some of the details of these cells a little bit later. And then by the time we get to the papillary duct, our cell composition is changed into these more columnar cells here. All right, so we have cortical nephrons, which are 85% of the nephrons, and these, most of them remain within the cortex, and only a very small portion of the loop of Henle is going to dip into the medulla. The juxtamedullary nephrons are about 15% of our nephrons, and their nephron loops are going to go way down deep into the medulla. And they're not just going to have peritubular capillaries that surround the renal tubuli like we have in the cortical nephrons. They will have peritubular capillaries that will then give rise to these things called the vasorecta. And the vasorecta are these straight blood vessels that are going to be paralleling these long loops of Henle, so these long straight loops. And these are going to be very important, as we'll see later on, for resorption of water. And this is going to be important for concentrating the urine. So one of the things we don't want to do is dehydrate ourselves. So we want to make sure that we recapture enough water to return to circulation, to be part of the plasma. So if we lose too much water, we would dehydrate. So the nephrons are going to play a very important role. Now the cortical nephrons perform almost the same functions as the juxtamedullary nephrons, secretion, absorption, these kinds of things, but we're really going to have the concentration of urine within the juxtamedullary nephrons. All right, so here's a picture. Here's a cortical nephron. Here you can see that here's our glomerulus, here's our afferent and efferent arteriole. Here is our proximal convoluted tubule, our loop of Henle, and here they've shown how the distal convoluted tubule is folded back and will actually make kind of an intersection here with the afferent and efferent arterioles before it then leads into a collecting duct. So here's our collecting duct. And then here's our papillary duct down here. We've got several collecting ducts leading into it. You will notice that the cortical nephron has only a very small part of the loop of Henle within the renal pyramid. Over here, here's our juxtamedullary nephron, once again juxtaposed to the medulla, so juxtamedullary. And it's got a very similar structure, except the loop of Henle is a lot longer and goes much, much deeper into the renal pyramid. All right, so now let's have a look at the blood vessels. Here's our afferent arteriole leading into the glomerulus. Here's our efferent arteriole, which will come out and give rise to these peritubular capillaries that surround the renal tubule. And you can see they surround the loop of Henle, and this is a cortical nephron. Now over here, we have our afferent arteriole, our efferent arteriole, and notice how the distal convoluted tubule comes in between them. And then we're going to have our peritubular capillaries up here, but then that's going to give rise to this long set of blood vessels called the vasorecta, which are going to surround the nephron loop in the juxtamedullary nephrons. And of course, as before, our distal convoluted tubule is quite convoluted and will eventually end up into the collecting duct, which will then end up in a papillary duct. All right. So when you look at the renal corpuscle, it's going to be very small, about 150 to 250 micrometers in diameter. So this is going, as we said, the initial segment of the renal tubuli, that will be the proximal convoluted tubuli, will be directly adjoined to it. And one of the things that's going to be very important is you will see that the glomerulus is directly connected to the proximal convoluted tubuli, and it's kind of hard to distinguish. If you follow it here, you can sort of follow it, and you can see that it then gives rise to the vasorecta in this case, and then as the vasorecta, or sorry, the nephron loop, which is surrounded by the vasorecta, so the nephron loop, and then as the ascending limb of the nephron loop is coming back towards the cortical surface, then it's going to give rise to our distal convoluted tubuli, which makes this nice little interface here between the afferent and efferent arterioles. And it is in here that we will have our juxtaglomerular complex, which will regulate a lot of the blood flow and other things, and it will also produce certain hormones that we'll look at later on. Now, then we have our distal convoluted tubuli that we can now follow. Where did it go? So our distal convoluted tubuli, which is now here, goes around, there it is, and we can follow it out to the collecting duct. All right, so the glomerulus literally is a knot of capillaries, and this is where filtration is going to happen. So the outer wall is going to be lined by a simple squamous, what we call capsular epithelium, that is continuous with the visceral epithelium that covers the glomerular capillaries. So the outer wall of our renal corpuscle, our Bowman's capsule, is a simple squamous capsular epithelium. And then that's going to be continuous with this visceral epithelium that covers the glomerular capillaries, and this is comprised of our podocytes. And then we have our capsular space, and this is where the filtrate is going to go when the blood plasma is filtered through the glomerulus. So, all right, so we've got our podocytes we've talked about. These are large cells with complex processes called feet or pedicels that will wrap around a specialized dense layer of our glomerular capillaries, as we've discussed before. The podocytes will be like this, and they will make these filtration slits through which the filtrate will pass. And what we will see is that each layer within the filtration membrane is getting progressively less permeable. So smaller and smaller solutes are filtered through at each level. So the fairly large things can get through the fenestrated epithelium. The dense layer makes a slightly more selective barrier, and then finally the podocytes are going to make the most selective barrier. And by the time the filtrate has gotten through the podocytes and into the capsular space, we will find that nearly all plasma proteins will be filtered out. There may be a few albumins left, but most all the plasma proteins are filtered out.